Okay, hello everybody. Welcome to my talk about secure containers for developers. I'm going to talk about what containers actually are, what is making them secure, and how you can use them, especially with a special focus on software developers. And I'm trying to go beyond that technology that everyone of you is thinking about when they hear the word container, but I'll come to that in a minute. Okay, let's start with a quick historic view about how containers actually came to be, and also where the name comes from, because that's quite interesting. Because when we think about container today, most of you will have Docker in their minds probably, and they will have this picture of a container ship that is often distributed along articles about containers, because containers are meant to be because they have a similar form and you can stack them on top of each other to utilize a system. But that's not actually where the name is coming from. The technology emerged in the 1980s when change root became a quite regular software used by system administrators, used to contain a server process. So originally it was developed for FTP servers, later on mostly web servers. And what it was there for was to limit the view a process or a server process had on the file system of the server. So if anyone could break out of the server or could access files with the permissions of the server, they would not be able to break out of this containment and see files in different parts of the server which are not meant for this process. So the word doesn't come from the stackable container, but from containing a process, limiting its possibilities. Yeah, that was the beginning of it, and it became especially interesting in the early 2000s. The development was more or less parallel to that of the virtualization technology that came to place with the rise of VMware originally, and more powerful x86 architecture servers and PCs. And containers arose because those virtualization technologies were quite heavyweight, well fit for servers, but not so much for PCs. And the people looked out for more lightweight alternatives which could reuse more resources from the host system and therefore be a lot faster and more memory efficient. I've listed you here a list of important technologies that led this development. In 2000, Virtuoso for Linux, which later became OpenVZ, which is still somehow around. And then BSD came jail, Zones on Solaris, Linux vServer. Most of them are quite defunct today and have been replaced by newer technologies, which I will talk about later on. Co-developed technologies which were essential for deploying those containers in the Linux world were some security features present direct in the Linux kernel, namely the access control systems AppArmor and SELinux, and namespaces and cgroups all in the early 2000s, more or less. I will explain a little bit later what these technologies actually are. And finally, in 2008, the technology that I will talk about mostly today, the Linux container system, LXC, was created, which was more or less a collection of a user interface for those technologies, for those security technologies mentioned above. And most important, what set them apart from the other systems which I had on the previous slide, like vServer and OpenVZ, is that all that was necessary to use it was included directly into the mainline Linux kernel, and no modification, no extra modules or whatsoever was necessary, which was quite great for the adoption of it. And then, of course, in 2013, a company called .cloud initially came around, which was later renamed to the most famous Docker that we know today, and which is the most common use case of containers in the Linux world. These days, what's interesting is that Docker was originally based on LXC, on the Linux container systems, but they switched to a different library a few years later on, but in the back, it is still using those very containment features that I mentioned above, like the namespaces and the cgroups and the security extensions of the kernel. Okay, what are containers and what terminology do we need to know, and how do they differ from other technologies? Let's talk about what a container is as opposed to a virtual machine as provided by KVM or VMware or VirtualBox. Well, a virtual machine is running a full operating system. So it's emulating, or virtualizing to be precise, a complete set of hardware. And then you have some storage, on which you can install a complete operating system. This can be Linux, this can be Windows, this can be macOS, a BSD system, whatever you like. And which is then fully separated from the kernel by the hypervisor. As opposed to that, a container is running within the host operating system. So a Linux container shares the kernel with the host kernel, uses the same kernel as that of the host. And it also reuses a lot of the interfaces, hardware interfaces that is provided to it, which has the advantage of it becoming more lightweight, which has the disadvantage of a weaker separation, which might cause a few security problems. Yeah, but what you get is that you need less storage space, less memory, and especially a much faster startup time. If you want to create a new virtual machine, even if you can clone from an existing one, that's usually a task that takes minutes. Booting up a virtual machine takes tens of seconds, while a new container is created within a second or two, and the boot up time is almost instant. So it's a lot faster and a lot easier to deploy new containers and create a lot of them on your systems, where with virtual machines, you have to limit yourself and really plan ahead how many of them you want and how you should deploy them. One very interesting difference exists between system and application containers. That's something that's not talked about a lot, so you probably will not have heard of this. Both of them are names for containers which can be based on the same technology, but they're meant for different use cases. An application container is what you know from Docker. An application container runs a single process, a single program, and the lifecycle of the container is tied to that single process. So the container starts when the process starts, and when the process stops, the container stops. While a system container, which is what LXD is for, which I'm going to talking about today, is more similar to the lifecycle of a classic virtual machine. It's meant for a long-living container, which can run multiple processes and which you can access just like you can a virtual machine. So you can SSH into it, you can get a shell in it, you can install software in it, you will update it, and you can use it more or less for the same task as you would as a virtual machine, but again, faster and with less memory requirements. For a very important thing for security of containers is the concept of a privileged container. A container in the Linux world can either be privileged or unprivileged, and the difference is what happens with the root process within the container. Inside the container, you have a view of users in the systems, and you have a root user within the container, and the process, since it's all running on the host systems in reality, has to run under a certain user ID. And if the process is running as root with root privileges on the host system as well, then we're talking of a privileged container. It has the privilege to run root process on the host. An unprivileged container does not have these capabilities. So even if it looks like it run to the inside of the container that root is running a process, on the outside, on the host system, it is running with an unprivileged user ID and can thus cause a lot less harm in case of a breakout. So whenever you have a choice to do it, you should always start an unprivileged container. As for the technologies that I mentioned before, Docker still defaults to privileged containers, while LXD these days default to unprivileged containers. It wasn't always the case, but it's true for a few years now. So how do these technologies, which are the base of containers, work? The probably most famous one of this is namespaces. And the Linux kernel can create namespaces for various resources like process IDs or user IDs or a mount space, which limits the parts that a process can see of the system. So one process can have a completely separate set of user IDs or can have a completely separate set of process IDs available. And this is how you manage it, that the processes that you see in the container are of a different set than the ones you're seeing on the outside, and one container can never see the processes that are run on the host system or on a different container, and the users are different as well. cgroups are not so much there for isolation, but for performance optimization. With it, you can define which system resources your host is allowed to have, how much memory it can use, how much CPU time it gets, as opposed to different containers. By default, this is usually set to an equal distribution, so every container has the full access to all the resources, but you can limit it if you're running a lot of containers which are there for different purposes. Then there are the access control security extensions, namely SELinux and AppArmor, which can augment a modern Linux system with mandatory access control systems. In a typical Unix system, you just have discretionary access control rights to files. Every file has a user and a group with read or write or executable access, and the user owning the file or the directory is allowed to pass access of it to a different user, to a different group. With mandatory access control systems, those permissions can be limited by a central set of rules which are configured in the system and which cannot be overridden by the user, even by the owner of the file. And what is quite interesting about it, it can even limit what root is allowed to do. So even a process running as root, it may not have full access to the systems because an AppArmor rule forbids it. That's something that you're usually not configuring manually, but the distributions are usually using it in the background. And if you're running LXD on a Debian system, say, then AppArmor is running in the background with pre-configured rules in order to prevent the breakout from the container. Yeah, so let's come to the most important part of this talk, what Linux containers are and how they work. And I'm going to give you a short tutorial so that you can, which you hopefully will be able to reuse and to start using Linux containers right away. Yeah, LXD, I've already said it, is a user space interface for the Linux kernel containment features. It provides an API and command line tools to actually use it. So it's an interface for these kernel features. There are a couple of front ends to use LXD. It has a library and a command line tool set named LXD utils, which is not very comfortable to use. I will show you an alternative on the next slide. And there are also a few hypervisor-based front ends like libvirt, which is mostly used by KVM, but can use LXD as well. Proxmox is a more enterprise-ready virtualization system similar to VMware vSphere, but an open source software which can also create LXD containers. And then finally, there's a more user-friendly front end named LXD, which is what I'm going to show you right away. LXD is, as I said, a more user-friendly front end with a few added capabilities of LXD. It is developed by Canonical, the software distributing the Ubuntu Linux distribution, and it's quite nice to use. LXD provides a network daemon, which can be accessible via IP networking or via a Unix socket if you're only running it locally. And then you have a command line tool to consume this API. This tool is for some unfathomable reason not called LXD, but LXC, which is quite can be quite confusing, but that's the way it is. Of course, you can use the REST API via a browser or different or direct HTTP calls as well, but that's rather unusual. Yeah, what you're doing is, as opposed to a virtual machine, you're not installing a new operating system, but you're getting a base image for a distribution you want to use, and then you're just cloning this image to start a new container. There are online repositories which will give you access to a wide range of those images. Why is the thing interesting for software developers? Well, the first use case, which I quite like, is to have an isolated execution environment of your application. So if you're running a server and you want to run multiple different services, you can run each of them in a separate LXD container or LXC container, and they won't be able to interfere with each other. Similar to what Docker is doing if you're hosting every process in a Docker container, but it's allowing you more manual or traditional system administration access to those containers. For developers, it's quite nice to have a reproducible development environment. You can have for each software that you're developing or for each language that you're developing in, you can have a separate dev environment with separated dependencies. Because these days, for most languages, you have a quite complex dependency managers like NPM for JavaScript development or pip for Python, which is installing quite a lot of dependencies on your systems. And if you're not very careful, these dependencies managers might very well destroy the software installed in your host, and the dependencies can interfere from one project to each other. So with LXC, you can have a separate container with separate dependencies for each project. It's basically free from storage and memory cost, and they won't be able to interfere with each other. And if the dependencies ever get out of hand and there's too much installed on the container systems, you can just start a new container. It's especially nice if you're able to make yourself a reproducible environment with a technology like Ansible, but that's a different matter. And of course, one thing that's also nice is software testing, because if you're having, again, an Ansible rule to deploy your server, or which we would use to deploy the software to a server, you can use this playbook to create a very similar or almost identical environment on your systems where you can test your software on, which is, yeah, quite comfortable. Okay, final part of this talk, I will show you a quick tutorial to LXC and show you that it's quite simple to get started with it. So maybe you can try it out later on. So as I said, LXD is developed by Canonical, the software, the company behind Ubuntu. So it's included in Ubuntu since quite a few releases. For if you want to use it on a different distribution than Snap, the packaging technology also provided by Canonical is used. There are a couple of packages, just install them and you're good to go. There's quite a lot of good documentation. Here you have the links. So what do I do to get started? The first command that I'm running is LXD init, which initializes my software. It creates a network with NAT capabilities to reach the internet. It creates a storage pool where the images are stored, and a couple of other things. For most users and for trying it out first, you can just take the default values for everything. As I said, you need a remote to create a container. There are a couple of remotes pre-configured, one from Ubuntu directly for the different versions of Ubuntu, and a more generic images repository for different distributions. You can list the images available in a remote. The semantic of the command is quite similar to what you used from Docker maybe, or from the IP command. The commands always start with LXC, then you have the subcommand and the subcommand again and again. And you can always use help for each level of the command to get a very concise explanation of what you can do with this step. So LXD image list Ubuntu lists all images in the Ubuntu remote, and LXD image list images lists all images in the images remote. As I said, images, you have pre-configured images for almost every Linux distribution out there, like Alpine here, or Debian, or even Kali Linux for pen testing purposes. If you want to launch a new container, then then this is the command to go, LXD launch, and then we're giving it the name of the image and a name of a new container. And if the image is already present on your server, so if you've already downloaded it and cached it, then this creation of the container doesn't even take 2 seconds. It's extremely fast. With LXD list, we get a list of all containers running. We're getting an IP address automatically. And with LXD access, we get a shell. And we're in it. It's, as I said, it's a system container. It can be used just like a virtual machine, and you have a new container set up in a few seconds, which is quite great. And you can just test your stuff fast, and then maybe destroy the container later on if you don't need it anymore. Yeah, we can create a new storage pool if you don't want to store the storage just within a directory, but within a BTRFS or ZFS pool. We can do so, which is nice because it uses deduplication, and the containers will use less storage on your host system. An interesting concept are profiles. With profiles, I can set quite a lot. I can preset quite a lot of configuration for new containers. For instance, I can use Cloud Init, which is a software to initialize new virtual machines or containers. And this is a rule set, for instance, that you can use to deploy an SSH key straight away on your system. So what is this set of commands is doing? Whenever a new container is created using this profile, then a user called Ubuntu is created, and the following SSH public keys added to the authorized keys file within the container. So you must not use the LXD access syntax that I've shown you before, but you can instead use SSH to connect to the server and to get a shell. We can also do shared directories. As I said, if you want to use it as a development machine, you will probably want a source code directory which is shared with your host system, and you can add a folder as a new device to a container like this. To be honest, this is just half the truth. If you want to actually use it in a non-privileged container setting, then you will have to do a few more commands to get the permissions right with POSIX ACLs, for instance, or with UID mapping, but there are quite good, there's quite good documentation on this, on the links that I've given you before. And if a container is done like this with the profile, then the authorized key file is added to it, and we can SSH into the container. Yeah. A few more things that we can do to wrap it up. We can also create different networks, like with a virtualization hypervisor. We can have multiple interfaces. They can be bridged to a physical device on your host, or they can be completely virtual with access to the outside world of the internet, or a really isolated network which only allows the different containers to communicate with each other or with the host systems. Here you have the commands to create an isolated networks. LXD network creates a new network which has a name, and we're setting a few configuration options. We're disallowing NAT to connect to the internet. We're disabling IPv6. And if all of that is done, then we can just attach the network to a new container, and it will be able to communicate with other containers using this network interface, but it won't be reachable from the outside world, and it won't be able to reach the internet through this network interface. I mentioned privileged containers before. There's a configuration setting to check if a container is privileged and to make it privileged in case you need it. there are a few things where you can't get the permissions with for non-privileged containers, and that's how you set the configuration option, LXD config set, container name, and what you want to set. With config show, you're getting all the configuration options. And that's the final slide. That's the final slide. It shows how this privileged container setting influences the user ID of the container. If you look closely at the beginning of the slide, I am making the container web dev privileged, and then I'm starting a process in it, like a tail process as root within the container. And if I'm checking on the outside with PS and which user ID this process uses, then I'm seeing that it's using root on the host system as well, which is allowed because the container is privileged. Now I'm setting the container to unprivileged, set security privilege to false. I'm starting the same tail process again as root in the container. And in the last line, you see that the user is not root on the outside now, but rather has the user ID 165,536, which is a totally unprivileged user, not able to do any harm on the host system. And that wraps it up. I'm welcome to any questions that you have and help you further with your introduction to the LXD world, which is quite interesting. It's a technology that is really great and which would deserve more attention and more users because it's quite capable and can help you a lot in your day-to-day tasks on Unix systems.